In this video, we are going to look at string matching algorithms. Okay, so this is a problem description. We have a input string, which is a string over an alphabet. So let's call it T. So here starts from 1 to n. And then we have a pattern string. We call it P. And it's from 1 to m. So what I really want is to find out how many occurrences of P in T. So then, for instance, if here is a P, so this is P, sorry, go over here. And then we're calling 1 as a shift position. And then if we start from here, that's another P. So this is another P. Then this is another shift position. So finding all appearances of P is equivalent to indicating all these shifts. Okay, so that's what we are going to find. So for instance, in this example, the pattern is AB, AA, and this is your input string, and you find that ABAA appears in here. So the position, well, the position here is actually equal to, okay, so so this is S plus I, so this is 4. Okay, so I starts from 1, so this is a 4. Okay, so the position here is up here, so the one cell before the actual pattern begins. So S is equal to 3. Okay, so that's what we are looking at. So this is what shift S means. Okay, so one cell before S. Okay, so that means the pattern begins at S plus 1. Okay, so this is where the pattern begins. So this is at S plus 1. Okay, so then this S is a shift. Okay, so again, we are going to look find all appearances of P in T. Okay, so we're going to look at 4 algorithms. A naive algorithm is straightforward, right? So you have a T, your input, you have P, so you start compare these cells one at a time, right? So you compare this, maybe I write it, let me write it in a different way. So okay. So this is my P. So we compare one cell at a time. So if all matches, then I found one. And then next, I'm going to shift to the next. So then I'm going to start here. So next, I'm going to start here, and I'm going to look at this P. So I shift one position to the right, and then again, I compare one at a time until my P goes in here. Okay, so this is until the end. So that means that I only need to look at n minus m plus 1. So because I don't have to shift, once I'm here, I don't need to consider the rest of this position. So in other words, I don't need to shift P over, because once you shift P over, you are off the boundary. So then there are n minus m plus 1 comparisons to do, and each comparison, you compare two m pairs of symbols, and hence this naive algorithm takes the order of n minus m plus 1 times m steps. So this is a quadratic algorithm. So this is a naive algorithm. Anybody knows how to write code for doing this. Okay, so this is a computing one, right? So this is a computing one task. So not interesting. And this pre-processing time is none. You don't need to pre-process it. All right, and then we're going to look at Rabin-Karp algorithm. So this algorithm involves pre-processing time, and running time in the worst case is still the same as the naive algorithm. But the good thing about this is the average running time is much shorter. Hence, it is a very useful. It is a useful algorithm in practice. So we're gonna look at that, and then we're gonna look at how we can use a finite automaton to do string matching, and that involves a construction of a finite automaton. So that's a pre-processing time, and the good thing about that is once you have a automaton, the matching time is linear, okay, in terms of n. Finally, we're going to look at Knuth-Morris-Pratt, or KMP algorithm. And this is based on finite automaton, but its processing time is shorter. And also it is a linear time. Matching is a linear matching time. Okay. So now we're going to start on Rabin-Karp algorithm. All right. So first, let's look at some properties of about overlapping suffixes. So this lemma says that suppose that x and y are both suffixes of a given string z. All right, so that means this. So I have a z. So this is input z, and then I have x. That's a suffix. So that means this portion is the same, or I have another. So this is x and y, right? So x could be longer than y, or y could be longer than x. So if x is shorter than y, so in other words, y is longer than x, then of course x will have to be a prefix. X will have to be a suffix of y. So that means that now y is longer. Y is longer. Now remember, this part is the same. So of course, x has to be a suffix of y. Of course, if y is shorter, then y will have to be, no, so if y is here, then y will have to be a suffix of x. And when x and y are equal, if and only if they have the same length. So because they are suffix of each other. Okay, so that's easy to see. So here is just lay out different cases that I already talk about here. So that's straightforward. So as you can see, drawing can help you understand many different things. So this is one of the examples that drawing helps a lot. All right, so next, well, we already mentioned this naive algorithm, right? So computing one algorithm, so nothing interesting. So let's now move on to the Rabin-Karp algorithm. Okay, so it performs well in practice, but as we said earlier, in the worst case, it still runs in big O of n minus m plus 1 times m steps. So I need to put a parenthesis here. But the advantage of this algorithm is that the average case running time is much faster. All right, so now let's look at the idea. So the idea here is that we are going to represent a string as a number. So we are going to represent T and P as numbers, actually as integers. Okay, so as integers. All right, so how do we do that? So first we're going to look at our alphabet. So let's say alphabet, we have a bunch of symbols. So let's call it, let's say we have these symbols. Then we can corresponding to then we can use this D as a radius D notation. So that means we use 0 to represent A1, 1 for A2, until D minus 1 for AD, right? So for instance, if D is equal to 10, we're going to use our decimal system, right? Decimal number, so that we use digit 0, 1 up to 9. Okay, so that is called the radius D notation. Okay, so once we have this, then we can represent a we can represent input T and P as a number in the following way. So for instance, we can write P. So this P1, P2 up to Pm can be represented as a number in this system, in the radius D system. Okay, so which of course, you know, it is just a polynomial, and with D here to indicate that the significance of a particular bit. Okay, so that's a polynomial. And similarly, we can represent a portion of T from S plus 1 to S plus M as a number. Then we call that TS. So that's a number. P is a number. So that means we reduce the comparison of two arrays into a comparison of two numbers. So comparing two numbers, as long as they are within a word length, then comparison is just one step instead of m steps. Okay, so that is the time gain we can get. All right, so that's the idea. All right, so now let's analyze the runtime of Rabin-Karp. So we know that Rabin-Karp reduces the comparison of two arrays of size m into comparing of two numbers of length m. Okay, so if this m is small enough, for instance, say you have, let's say we can, so this m we can convert. Now let's look at the extreme case. So let's say if d is equal to 2, so we can use a binary number to represent your input string and the pattern string. And then if m is, let's say we are looking at a 64-bit machine, that means a word size is 64 bits. So if m is less than or equal to 64, so then comparing two arrays or two strings of length m is reduced to comparison of two numbers. Okay, two numbers in one in a word. So that comparison takes one step only. So that's a Rabin-Karp. So now we are going to analyze now, because you have so we have to consider the time to convert a string into a number to give them value. Okay, so that means it's no longer a string of characters, it becomes a number. So that conversion needs to carry out an evaluation of a polynomial on value d. Okay, so this is evaluation. But in the last video, when we talk about evaluation of a polynomial, we look at the Horner's rule. So we know that evaluation can be done in linear time. So that in big zeta of m. So then now this is for p, but if t is long, right? If t is long, so you compare this part into a number, and then you compare this part into a number. You compare this part into a number. So how many of those? Okay, you actually still have n minus m plus 1. Many arrays, you need to convert them into numbers. So if each time you start from scratch, so that still takes this many times, this many steps to convert these substrings into numbers, which then, of course, you don't really gain much. But fortunately, what we need to do is that once we compute the first conversion, the rest of the conversion does not need m steps. Instead, it only needs constant steps. Okay, so that means that we only need a big zeta of this many steps to convert, and of course a plus m, because the first one you still need m, so that's really a big zeta of n, right? So this is a big zeta of n. So let me clean this up a little bit. Okay, so this is n plus 1 plus the first one, so that's n. So this is big O of n. So you only need linear time to convert these substrings in T into numbers. So the proof is just some manipulation. So let's say I have TS. Okay, so this S of course starts from 1, right? So let's say I have already figured out TS. And then in order to do TS plus 1, we don't need to start TS plus 1 from scratch. Instead, we are going to use TS. So this is how. Okay, so maybe, okay, this is how. So say TS is equal to, maybe open up a screen, okay. So we start from TS, and then this is the most significant bit. So that's D n minus 1 plus T S plus 2. This is D n minus 2 plus T of S plus n minus 1 D, and then plus T of S plus M. That is the least significant bit. So that is TS. Let's say we already knew this. For instance, at the beginning, T will start from 0, right? So T0. So it takes this many steps. And then we can compute T1 from T0, and then T2 from T1, and so on until we have T n minus n plus 1. So that is from the one before, right? So that is the idea. So let's say we have this already computed. So now I'm going to compute at TS plus 1 from TS. So now we know that TS plus 1 is equal to TS plus 2. Okay, that's Dn minus 1 plus Ts plus 3, Dn minus 2 plus Ts plus m. We've got D here, and then plus Ts plus m plus 1. So that is the least significant bit. So now let's see what we have over here. So let's compare TS and TS plus 1. So you see that we have the same term T of S plus 2, T of S plus 2, except that this is D to the m minus 1. This is D to the m minus 2. So if we multiply TS by D, okay, so what do we have? So now we can see that TS times D, then we have this TS plus 1, D to the m's power. Now it's just one multiplication here, right? Remember, each of these TS fits in one word, and D also fits in one word. Then we get, so maybe I can rewrite it so that we can line that one up. can see better. Okay, so let's do it again. So let me do this way. So I will write this so I can have some more room here. So TS plus 1 is equal to this. And then I multiply D with TS. Then what I have is TS plus 1 D to the M, right? So from here. And then TS plus 2 D to the M minus 2. So as you can see, this is D to the M minus 2. We'll keep on doing. And then the last term is TS plus MD. So that's what we have. Okay, so now in order to get to, I'm sorry, this is 1, right? So this is 1. This is minus 1, sorry. So these part can be canceled, it can cancel each other. They just canceled. Okay, so that and TS plus 1 then is equal to T. So now we still have this one. So that's T. So we just use whatever that symbol as its digit plus 1. So TS plus 1 minus DT will be equal to this guy minus that. So that's minus TS plus 1 dm, and then plus d times ts. Oops. Okay, so we can rewrite it a little bit. So we can actually, this is equal to d. So we take the d out. So that's ts. That's we already knew. And then minus ts plus 1 d to the m minus 1 plus t of s plus m plus 4. Now we already know ts, and what is ts plus 1 dm minus 1? So which is just the most significant digit of ts. For instance, you write ts. So this is m bit number, right? So this is n digit. So this is not m bit. So this is a number of length m. So this is the most significant bit. So you put everything else 0. Then this is ts plus 1 dm minus 1. Okay, so that number is obtained from ts also. So as you can see, if we know ts, then we immediately know this number. So then, so we use 1 subtraction, 1 addition, and 1 multiplication. So that means that ts plus 1 can be obtained from ts in constant steps, right? 3 and then time. So there's 3 operations. Each operation takes let's say, because this is a word at the word level operation, so it's just a constant time. Okay. Okay, so, but of course, Rabin-Karp algorithm works well only when P is not big. So in other words, this M is not large, okay? So it can fit in a word, then also TS, right? So both P and TS cannot be too big as long as they can be, they can fit in a word, a computer word, then the calculation is efficient. But of course, in practice or in the in applications, they could be big. Okay, so how do we solve this problem? To solve this problem, of course, we can just sort of like, okay, what happens if we take a modular operation and reduce the size of P and the size of TS? So that's the idea. So we're going to select Q as a modulus, and then we take P mod Q and TS mod Q. So then to make sure there's a fit in one computer word, and TS mod Q also fits in one computer word, then we can just use a comparison of two numbers. Okay, so that still takes constant step, constant time. So then what happens here is that we want to choose Q, okay, such that D times Q just fits in one computer word. Okay, so D is the number of the alphabet. So that is really, for instance, using decimal, the alphabet has 10 symbols. D is 10, so 10 times Q. So that fits in one computer word. So now remember, a 60-bit word can hold a number in values up to 2 to the 64 power. This is a binary, right? So that could still be very large. Okay, so that's how we choose Q, based on the inputs at hand. All right, so, and then after we do modular Q, so let's say TS plus 1, then as we said earlier, so this is TS plus 1 is equal to D times TS minus TS plus 1 times times H, and H here is congruent to D to the n minus 1 mod Q. And then plus TS plus n plus 1 mod Q. So then we use this to compare with P. So we compare, so this is of course the modular Q. So after that we compare them. So then, so if they are equal, right? So comparison, okay, so they are equal. That means the TS is congruent to P mod Q, but it does not imply that they are actually equal. They are equal under this modulus Q. So it does not imply they are equal. But if they are not equal, so if they are not equal, then we definitely know when you remove this modular Q, the original numbers are still not equal, because if the original number is equal under modular Q, they have to be equal also. So that means that when we do this comparison, if they are equal, then we have to check further, okay? Check further to see whether the original numbers are still the same. If it's much too big, then you can just compute. You just compare the strings, the original string. But if they are not equal, then we don't have to do anything further. So this really means that in the worst case, let's say all of them, a lot of them are equal, then you still have to, each comparison may still need to do m steps. So then you have this many strings, you have this many strings to compare. So in the worst case, it is still the same time bound as the naive algorithm. Okay, so you compare. So in the worst case, right, you can imagine all of these pair under modular Q, they are equal. So then you have to check whether the original strings are actually equal because they are much too big. So you still have to compare the strings. So that is the worst case. But you can imagine in reality, this worst case situation may not happen often. So then that, okay. Let's look at the average running time or expected runtime. So assume that there are V valid shifts. So that means that this V is the ones that we have. TS is congruent to P mod Q, so they are valid. So now we need to compare whether their original strings are the same, right? So assume we have V many such pairs, okay? Then the probability that this is true, but this is not true, is 1 over Q. Okay, so this is the so it's a 1 over Q. Now, of course, this result is non-trivial to prove, so we are not proving it here. So in other words, what we are trying to say here is that if you see TS is congruent to P mod Q, but TS is not in P, so we know the odds that happen is only 1 over Q. Then, of course, the expected running time will be big O plus big O of M, and you have this many valid points, and then what you are doing in expected time is plus N over Q. Okay, so that's N over Q. So that means that when you don't have too many valid shifts, in this particular case, let's say you only have constant valid shifts, okay? Sometimes this is only maybe 1 or 2 appearances of the pattern in the string. And so that would be constant. And also Q is greater than or equal to M, all right? Then well, M is a length, so this is often true, right? Q is the value, Q is a value, M is a length, okay? Now, remember the length of M, the value of it could be up to 2 to the M. So this is often true. So as long as this is true, then we have a linear time algorithm. Okay, so this goes to linear. So this goes to linear time. All right, so that is the end of the Rabin-Karp algorithm.